The main objective of this mission is to study a planetary system that are similar to our solar system and to characterize exoplanets. So, well, this week we are having, actually today still is going on the Plateau week. So I'm going to show here some results that are up to date, really fresh, some of the results that were presented yesterday. But first, I will introduce a little bit the science objectives and the methodology used by Plateau, the Plateau consortium. So this mission will be launched at the end of 2026, still on date. And Plateau will answer the scientific question: how do planets and planetary systems form and evolve? And is our solar system special, or are there other systems like ours? And are there potentially habitable planets? So this to address these three scientific questions, we need to study the planetary system, but we also need accuracy in stellar properties, because most of what we know about planets is derived from the hosting stars. So more specifically, the science objectives are to obtain bulk properties of thousands of exoplanets, including terrestrial exoplanets in the habitable zone of sun-like stars. For that, the required planet property accuracies are an error of less than 5% in the radius of the exoplanets, less than 10% in the mass, and less than 10% in the edges of the planets. That's it for an Earth-sized planet orbiting a G0 dwarf star with magnitude brighter than 11. So Plato is going to observe very bright stars. In that sense, is quite different to other past missions like Kepler, which studied stars fainter than 12 magnitudes, between 12 and 16 magnitudes. And the other science objective is to study the internal structure and evolutionary state of hundreds of thousands of stars. So why do we want to do such studies? Well, first, because we want to know the architecture, formation, and evolution of planetary systems, and we want to get correlation studies with the stellar parameters. So on the other side, there's a stellar pulsation. We can study stellar pulsation to obtain precise stellar parameters, to study the internal structure of the stars and their evolution. For the propagation of the stellar pulsation, provide the D modes, gravity modes, or pressure modes, provide us internal rotation profiles, and is basically the study of stellar pulsation is the only way we have to get information from stellar interiors. So Plateau is going to focus on solar-like stars and late type stars, this part of the HR diagram, but there will be also a complementary science program where other stars will be observed too. We are especially interested in classical pulsators, pulsating stars in the classical stability strip, like Delta Scuti, Cepheids, Gamma Rho P, and also Gamma Doradus stars. But Plato is not the only mission doing exoplanet studies, and there's also this other missions from the European Space Agency, more focused on the exoplanet atmospheres, not doing asteroseismology, but they are there's a very nice synergy between Plato and these other missions, the James Webb Telescope, the CHEOPS and Ariel, that will be launched in a few years. It's not the first one. It's not the first mission who has done that, of course. Here you can see the past ESA mission, successful, like CoRoT, Gaia, CHEOPS is still working, and Ariel will come later. And then these are NASA missions, very successful, like Kepler and TESS. That Kepler and TESS also did asteroseismology, but the characteristics of the mission are very different, as we will see. So about the methods, the methodology that the Plato scientists will use to achieve the objectives. So there are basically three methods: radial velocity, asteroseismology, and transit studies. So, for example, Kepler and TESS use asteroseismology combined with transits. But for Plato, radial velocity is going to be more important, because Plato is going to study bright stars. So it is feasible to perform ground-based observations, radial velocity observation for most of Plato targets. So I guess you probably know already how this method works, but well, basically the star with planets orbit the center of mass of the system, and when you see the star traveling away, the wavelengths are shifting to the red, and when the star is traveling towards us, then there's a shift toward the blue, so we can measure detect the exoplanet with that method. Asteroseismology, I already talked a little bit about that. Is the study of stellar pulsation, and different frequencies probe different radius of the star, so we can get the internal properties at different depths. But we can also get the mass and the radius and the edges of the stars through asteroseismology by fitting stellar models and using scaling relations. I would show an example now. And the transit is the more obvious of these techniques. It's just the dip in the light curve. So asteroseismology and transit studies are both based on brightness variations. You just need the brightness variation, which is called the light curves of the stars. So this is an example of an asteroseismic study of a solar-like star. This 16 Cygnus A star observed by Kepler satellite. So you can see that this is the Fourier Transform, the power spectrum of the light curve gathered by Kepler, the Kepler satellite. So when you perform the Fourier Transform, you get these many peaks, and each peaks correspond with a pulsation frequency. So the more frequencies you get, the better your models will be, and more information you will get from the star. But in the case of solar-like stars, you have several advantages. For example, there are these periodicities between frequencies, which give you this frequency separation, large frequency separation, that it relates. It's linked directly to the mass and radius of a star. So you can determine the mass and radius of the star by using this scaling relation. There are several scaling relations for solar-like stars, also using the frequency of the maximum or these other periodicities called the small frequency separation. As you can see here, a sum of this. This is the large frequency separation and the small frequency separation that also gives you some properties related to the core of the stars. Okay, so with asteroseismology, we can get the stellar mass, the radius, and the age of the star with scaling relation and stellar models fit into the spectrum. With transit studies, we can get the inclination of the orbit and the ratio between the radius of the planet and the radius of the star. So if we have the radius of the star with asteroseismology, we can derive here likely the radius of the planet with these two. And now we're using ground-based observation with radial velocity. We can get this ratio, and because we already have the inclination through transit studies and the stellar mass, we can derive here also the planet mass. So in the end, we get complete orbital parameters, density, and ages of exoplanets by combining these three techniques. But now, if we look to the confirmed exoplanets, there are many confirmed exoplanets, more than 5,000. Most of them come from Kepler observations, which I said before is for a star fainter than 12 magnitudes, between 12 and 16. There are also 7,000 candidates, adding CoRoT, Kepler K2, and TESS candidates. But we only have 100 or less than 100 exoplanets detected with mass and radius, for which the radius of the planet is less than 2 Earth radius. So those are the most interesting targets for Plateau, and we will change the paradigm of the planet studies, exoplanet studies, when Plateau is launched, because ground-based observation require magnitude brighter than 11, and Plateau will observe a lot of stars with that are very bright. So the stellar sample of Plateau, there's a core sample of 15,000 dwarfs and subgiants from spectral type F5 to K7 with magnitudes greater than 11, said before. So these are stars for which we can we can do asteroseismology, and many of them that, will be exoplanet hosts, but there will be also other stuff for stellar activity studies and different things. And the requirement for this is that for a star brighter than 10 magnitudes, 34 ppm per hour, and for a star brighter than 11, 50 ppm per hour of noise level. Then there's a statistical sample of more than 245,000 dwarfs and giants with magnitude brighter than 13. For those for that sample, we can do statistics. We can estimate the planet radius, for example, but there will be no radial velocities. They are too faint, and no asteroseismology. And there is also more than 5,000 late type stars and dwarfs that have been already observed by TESS. There is a nice synergy with TESS. We will extend the observation of TESS with Plateau. Apart from that, there is a guest observer program that will take the 8% of the observation time for Plateau. So here you can see in the H diagram the core program is here, this star, but you can also propose for the guest observer program. You can observe other stars, and you can do many things like combine asteroseismology with magnetism activity and flare studies, binarity, tides and rotation, distance scales and cluster, galactic archaeology, or even transits, gamma ray bursts, black holes. So the ESA call will be 9 months prior to launch of the guest observer program. So be prepared if you are interested. Now I'm going to talk now about the instruments and the Plateau mission in general. So Plateau have 24 telescopes which work simultaneously, observing a huge field of view. Each telescope has very large CCDs with 1 million electrons per pixel. This provides lighthouse with photometric accuracy better than 50 ppm. Long ultra stable monitoring of the same star without interruption. I use here the quotes because as we will see, there can be some gaps in the light curve. There might be some gaps. So the same star during more than two years. This allows 2 or 3 transits of an Earth analog. The launch mass is about 2.5 tons. The size is 3.5 times 3.6 times 3.7. The launch date is the end, still at the end of 2026, with an Ariane 6.2 rocket into the Lagrange point, the second Lagrange point. So there are 24 cameras with with a sampling time of 25 seconds, operating in white light, and 2 fast cameras with a sampling intervals of 2.5 seconds, operating in red and blue colors. So each camera has 4 CCDs, each of them with 20.3 megapixels. So these are the largest CCDs ever flown in a space mission. So the total is, because there are four CCDs, the total is 81 megapixels per focal plane. So that's it. That's 2 billion pixels in total. And the pixel size is 18 micrometers square. What you see here is the optical bench, the full optical bench of the telescope. This is a recent picture of the test that engineers are doing with Plateau. Now the data processing system are a very important part, and I'm very proud of this because it's the main electronic unit is being developed here at the IAA. So you can see here the main electronics unit, the main integrated with the rest of the units with a platform or service model. Well, the main electronic units, what it does is to receive data from the data processing units, which works with each camera, and process the data and send it to the central computer. So Plateau is going to correct and extract the light curves, all the light curves, the 100,000 light curves per camera on board, not on the ground like other missions did in the past. So for that, 12 powerful onboard computers are needed. So about the observational study strategy. Sorry. So you can see here the field of view, typical field of view, 2100 square degrees. The targets that are in the center will have more precision, and this is interesting. I hope you can see this well. Here's the Kepler field of view. The red square is CoRoT field of view. Then these yellow circles are the TESS continuous viewing zone. Is the region where TESS is observing the whole cycle, half a year. And this is the outer envelope of the field of the field for Plato. So this is the pink circle is the minimal field for Plato targets, and the green is the outer envelope. So you can notice here that Plato is going to observe much bigger regions of the sky, and for 2 years at least. So there will be, for the nominal science mission, there will be 2 long pointings lasting 2 years. And but this is not fixed yet. There is a possible alternative scenario, which is 1 long pointing for 3 years, and the final strategy will be decided 2 years before launch. That is probably next year. And if the mission is extended, 2 long pointings lasting 3 or 4 years will be included. So selection of the first long pointing sky field is it will be by June this year. The observation modes talk about the fast camera. with 2.5 sampling. These are the data products for the past camera, and these are the data products for the other camera. So for the moment, we have light course with 25 seconds of sampling, but there will be images also. This images is the name for what French people give to target pixel files in Kepler case, for example. So some news about the development status of the mission. So the payload module is completed. The payload module, the structural and thermal module tests are completed. Vibration test 2, and the flight manufacturing was released in October 2022. So just brief summary: the spacecraft progress is going well, and there have been some delays, but mitigated. So the integration will start in 2023 as planned, and the launch is still baseline for December 2026, with 4 months of ESA margin. So Plateau mission is still performing very well thanks to the combined effort of all teams. Now for the science part, the development status of the science algorithm system models have been the first version of these models have already been delivered to the Plateau data center for testing and integration. Now we are entering a phase of test with a prototype code actively being tested using simulated data. The first round of tests consists of functionality tests before proceeding with scientific and performance tests. So we are especially interested in the complementary science program because is where the classical pulsators will be studied. So the development status of this part of the mission is progressing too. So the activities largely center now around simulations. The team have been working on a set of massive simulations using the Plateau simulator to maximum to its maximum of capacity and functionality, to make sure that the simulated light curves cover the needs of the complementary science program. So the goal here is to get the community prepared in time for the launch, and I'm happy to answer the question like this one. If I have this group of interesting extragalactic objects whose magnitude distribution is peaks at 18, can you do that with Plato? That's what we are doing now. Okay, so now I'm going to focus on our team, Plateau IAA team. We have the technical team and scientific team. So I have to say that we are. I'm focusing here on Plateau IAA contribution, but we actually the Plateau project is involves also the University of Granada with PI Juan Carlos Suarez. I have to say that because he's there. So about the Plateau IAA, so the scientific team, the PI was Rafael Garrido, but he's now at honorem. So I'm leading now the scientific activities of the Plateau team as a postdoc. Jose Ramon is Mariela also postdoc, and we are waiting for a new postdoc, Sebastiano, a new and old postdoc here, known by many people, Sebastiano Francisis. Alejandro Ramon Ballesta is postdoc, he's in his last year of PhD. And Susana Martin Ruiz is also in Plateau team, but she's managing the sky quality office. It's more involved in the sky quality office. The technical team or PI is Julio Rodriguez Martin, and we have an increasing number of members in the technical team because of the more intense activity now, and because we are also participating in another mission, which I will talk about later. So that's Rosario Sanz, Carmen Pastor, Beatriz Aparicio, José Manuel Ramos, Juan Manuel Gómez, Nicolás Robles, Miguel Sánchez, and Gianpaolo Candini just arrived to the IAA. I hope I didn't forget anyone. Technological activity. So how the progress of technological activity from the Plateau IAA team. So this is a picture of the software for testing the reception of the 12 cameras and processing and sending to the central computer in a closed box. So here's the mail electronic units and the software they are developing. So here at the right is Nicolás Robles assembling the box with the data processing units inside. And you can see here the thermal and structural model of the main electronic units, black box. This is also new. This is from yesterday, I think. The new pictures, I mean, the electronic board for the EQM model. The scientific activities of the Plateau IAA team. We are mainly involved in these three working packages. This is inside the complementary science program, the working package of pulsating stars. That is focused on main sequence stars, the data analysis and modeling of main sequence stars hosting exoplanets, but also classical pulsators. So we are all involved in this working package here, and also there are some people involved in the working package determination of line darkening. We organized a workshop a few years ago about line darkening preparation, calculation preparation for Plato. And this is a preparation of light curves for asteroseismic analysis. This is what is taking me more time. I'm involved in the transit light removal for prepare the light curves to perform asteroseismology, because transits are hide the pulsations, produce a very strong signal in the power spectrum and a high pulsation. So we need to remove the transits before performing any frequency analysis for asteroseismology. So recently we have published this volume. It is a book called Challenges of Asteroseismology in the Era of the Space Mission, where several authors have published what is the more controversial in theory and data analysis in our field. And this is also a good preparation for Plato mission. So Antonio Garcia from the University of Granada and me were editors of this book, and to give some some pictures of this volume. This is a paper published by Alejandro, or a PhD student, where he applied this synchronous Cushing transform for the first time and detected some short time scale amplitude modulation in delta Scuti stars. This is the work of Marielle. She has found that stellar parameters can be estimated very precisely with the study of non-linearities in high amplitude delta Scuti stars. And this paper from Rafa Garrido, where I was involved too, the quaternionic transform is an alternative frequency analysis. Is extending the use of Fourier transform to quaternions, and it was quite interesting because we have found peaks where only was found noise before, with very high signal to noise ratio. So this is a very promising technique for detecting solar G modes. So I said before that I spend most of the time now with the preparation of analysis, preparation of light codes for the analysis for the asteroseismic analysis. So this is this is a pipeline we are developing for this working package, Plateau working package, and the goal is to develop and specify techniques and procedure needed to prepare light codes for stellar analysis, not only asteroseismology but also rotation and activity. So you can see here that this is a very big transit. So of course you cannot do asteroseismology with that light core. So we have to remove the transits and fill the gaps or model the transits and correct the light core with the many different ways of dealing with this. And this is an example of what we want as final project from this pipeline for asteroseismology. So it's a light core without no transits and no dips and no flares, and a very clean power spectrum with high signal to noise peaks. But this is the most complex submodel with many different algorithms interconnected. So this is these are the models for Plateau data correction, and this is the most complex. So the main worry is to ensure a proper transit removal without with preserving the original frequency content, and as fast as possible, because we are going to process thousands, tens of thousands of light cores. So here's an example of the algorithm I developed. So you can see the transits are corrected, are removed. You need, of course, you need the ephemerides, you need the orbital period for that. And then you remove the transit and you interpolate, and you get this nice light curve, which allows you to perform asteroseismic studies. Now I'm translating this into our language because MATLAB is not accepted by the PDs in the Plateau data center. So, synergies. So I talked about TESS before. With Plateau, we will have refined planetary radii, improved stellar ages, and extension of observed lines, which will allow to perform transit timing variations. And there will be also a nice synergy with James Webb, Ariel, ground-based characterization of atmosphere and the chemistry. And now HAYDN, which is the high precision, the satellite. We are just in the phase here of the proposal, and it will do high precision asteroseismology of dense stellar fields. So I'm going to talk a little bit about HAYDN because I think it's very interesting, and it also takes much time now for a group. So the HAYDN proposal was shortlisted last November. There are 5 missions shortlisted, and this year there will be an evaluation where only three missions will be selected. So we are meeting with ESA people now to fulfill the requirements of the European Space Agency. The PI of this mission is Andrea Miglio from the University of Bologna. Sorry, and there is a Spanish contribution from the University of Valencia, the IAA, the University of Granada, the ISC, the ICE, etc., etc. And the Spanish PI is Andrés Moya from the University of Valencia. And here the contact persons, Julio Rodriguez for the technological part and for the scientific part, myself. So what are the science goals of HAYDN? This is a next step for asteroseismic studies. If we have seen that there were exoplanet missions with some component of asteroseismology involved, now it's going to be more the opposite. It's going to be the main objective of the mission is going to be asteroseismology. There will be also exoplanet studies, but for the Voyage 2050 Senior Committee report of European Space Agency, there was this recommendation that a medium mission designed to carry out pure asteroseismology is desired. So this is HAYDN. HAYDN will do asteroseismology of stellar open and globular cluster control environments, and will produce breakthroughs in stellar and galactic science. So the main science goals are high precision stellar astrophysics, especially in the metal poor regime, evolution and formation of stellar clusters, and the assembly history and chemical evolution of the Milky Way bulge and nearby dwarf galaxies. Okay. So OPER's mission intended to observe a globular open cluster, but none of the previous space mission was properly designed for open clusters. So this is an important part, very important part of HAYDN mission. For Kepler, there are only 4 accessible clusters and 2 open clusters observed in an acceptable condition with a limited number of stars. And for K2, the mission following Kepler, there was 20 accessible clusters, 2 clusters observed in suboptimal condition. So the globular cluster M4 and the open cluster M67. So these are the main cluster that HAYDN will observe. There are other that are secondary, but these are the very populated, and they have very interesting science science objectives that I will not detail here, because probably I will do in the future a talk about this. I will not talk about that now because this is about Plateau mission. So, but you can see here that the PSF of HAYDN is much smaller than Kepler, even Plato or TESS. So this is designed for cluster studies. It's much better for dense stellar fields. The Spanish contribution is the third largest after France and Italy. So I said that all these institutes are involved, and we have a large expertise derived from previous projects in stellar physics, stellar modeling, stellar evolution, asteroseismology, seismic data analysis, stellar rotation, stellar activity, magnetism, galactic stellar population, galactic archaeology. Or we can take advantage of all this expertise and for HAYDN mission. And we have an instrumental contribution from IAA and from other centers. More specifically, the contribution of Plateau technological team is involved also in HAYDN for the data processing unit, and the PLC and the thermal stability. So with those acknowledgements, I finish here, and thank you very much for your attention.
Thank you, Javier. So now questions and comments.
Thank you, Javier, for your talk. Interesting, and for the overview of data. I'm curious about which is the level of uncertainty that you will get for the stellar parameters. Because several times you have said that actually it's going to provide the best accuracy so far, but you never provide an example with the current techniques. So which will the level of accuracy?
Well, it depends on the target. It depends on the observation you have. If you have longer observation, if you have a higher sampling, you will get more precision in your parameters. But well, the mission is designed to comply with this 10% minimum of 10% error when you use asteroseismology, because you don't have any other way to do that. So
well, the is the current accuracy that we can reach. For example, for all the test paper, we are having an accuracy for the stellar parameters of about 10% in radii, in radius, in masses, and so about 10%, 50%. So yes, we can go further, like maybe 5%. It could be a step forward if we can reach that level. It would be amazing.
Well, in TESS, you don't have such long baseline for the observation, like 2 years or more. So
I'm not sure. I mean, for TESS, we are not using asteroseismology for the stellar characterization. For TESS, we are using other techniques, another combination. So my point is, how in comparison of the stellar asteroseismology, in comparison with the current techniques that they've been used in other missions, like in TESS for us, for the characterization of the star, which is the improvement that you can bring now with Plato?
Yes, I think there's. I don't know if I have here. No. Oh, sorry. I had there's a plot where the precision is compared between Plato and I thought let me see. No, because I removed the Plato performance because it's already too long. Yes, the Plato performance is much better than TESS. It's comparable to Kepler. Kepler is the more precise mission, where you can get the smallest error for your stellar parameters. So Plato is going to be more or less like Kepler.
No, but but the stellar parameters are not obtained from TESS data. Stellar parameters are obtained from other techniques like spectra, so not directly from the light field of TESS. So I think that this will be the difference with PLATO, right? Because with PLATO you can obtain the stellar characterization directly from the light fields. We cannot do that.
Sorry, I thought that you were talking about the asteroseismic, getting the parameters to do asteroseismic.
Well, I mean, in comparison with the current techniques that we do with other missions, because we cannot apply asteroseismology in other missions taking TESS, we cannot obtain from there actually because of most of the stars are not pulsating. But yes, just to know the level of accuracy that you can reach with but it's okay. We can speak later about it if I'm interested in this level of accuracy.
I can show you the plot and you'll see.
Yeah.
I'm interested in the different samples that there are in Plateau. So you have like 15,000 like core sample, then you say the statistical sample. And then the envelope. So I would like to know why they are separated. Because it's separating things in terms of just brightness, or
yes, they are separated because of the brightness.
So you said for the statistical sample there would be no asteroseismology. Why is that? I mean, you still can do asteroseismology of very faint targets even on the ground. So I don't know if it refers to some tasks or the working groups.
Let me see. There it is. So for the statistical sample, you have fainter stars. So and the statistical sample is not aimed to perform asteroseismology. I don't think it's that you are too restricted, but it's not the main goal of this statistical sample. That's what I meant.
If they are to faint, you won't get any times in this video. What if you maybe on the but still you can go asteroseismology.
Yeah, but because they are fainter stars, then you cannot fulfill the requirements. So there's not this statistical sample is not aimed to do asteroseismology because you cannot.
So it's not referred to F5, phase 7, or something, or they are, but it's less money.
Yeah, let's see. Yeah, they are also F5 to K7 stars, but it's not here. Oh, okay. So they also dwarf and subgiants. The statistical sample is also dwarfs and subgiants. But as I said, the aim is not to perform asteroseismic studies, so because now you cannot fulfill the requirements, but you can still do many things with those light cores. You will get that because it will be they will have less precision, not only because of the brightness, because they are fainter, but also because they will be observed not in the center of the field. So the center of the field is the field is centered in the core sample, and you have the other stars populating in the envelope of the field.
And can you like how this, if they relate to that, or how is going to be the differences? Because you said there's this 3-year or maybe 3-year non-year observation, but I guess you have some differences along the way. And is it planned like this or so, like the movie or movie, and you're, I guess, going.
Yeah. Okay. Thank you for the question. Actually, it's not decided yet because some of us prefer the data is released openly as just at the moment it's gathered the Plateau data center, but other prefer that there's some period of commissioning, like 1 year or so. But I think it's not decided still. It's something we have to discuss. Maybe Juan Carlos have more information about that. I don't know.
Yes, it's about to be decided. It's being discussed in the PMC, the Plateau main board, and we have to decide it and publish. So we cannot say it right now, but well, it will be known very soon in the next months.
Mm-hmm. Okay.
Yes, a question related to the when you say that with this precision I have, very even if you have 1% of the precision in the solar, in the size of the star, you don't know how the moment is raised in the core. I mean, you don't know the rotation of the time, and you know a lot of everything that is ready. So we speak about the precision of temperature and gravity is enough. That target is not covered, and this can be applied to our sun. Our sun, you know, or every other know. And we know only 70% of the size. Gravity. I mean, the coding is unknown how it rotates, the rotation really starts. So I first would like to know how the sun is, because asteroseismic doesn't take into account this question, the question of the rotation. So what's the meaning of asteroseismic lines to answer? Today nothing, because we don't know what's the role of the rotation and how we interpret rotation seen through the sample, which is the path. Sorry to clarify if you already clarify.
Okay.
Okay, there is a comment by Eloy.
Un pequeño comentario respecto a la precisión, que si esos 50 partes por millón son un solo punto, lo están midiendo durante 1 hora, y esa es la precisión interna que obtienen. Así estoy súper. Es así, ¿no?
Un solo punto.
Está integrando durante 1 hora
Sí.
para una estrella de magnitud 11 y pierde 50 micromagnitudes de precisión interna. Esa es la. Si eso es así, quiere decir que cuando tenga 100 puntos, es decir, 4 días midiendo, tiene una precisión de 5 micromagnitudes en la curva de nube, en noise level. Y si está 1 año, 400 días, la precisión de la curva de la sigma, el noise level de la curva de luz, será 0.5 micromagnitudes. Quiere decir que entonces, para tener una señal significativa, en datos de Kepler, estoy aplicando un factor 5.6, quiere decir que cuando tú tengas en un periodograma, si el noise level está en 0.5 micromagnitudes, el nivel de significancia de una variable, de una pulsante, aplicando un factor para que sea bastante bien evidente para estrellas, para observaciones time series de tipo de misiones espaciales, el factor que es bueno no es 4, es mayor que 4. Particularmente estoy aplicando 5.6. Eso quiere decir que si existen pulsaciones o variabilidades por encima de 2.8 micromagnitudes van a salir significativas, con la observación de un año de observación. Si estás 2 años, entonces puedes encontrar baja significancia hasta 1.4 micromagnitudes de amplitud. Y si está los 4 años, pues puede bajar a 0.7 micromagnitudes. Eso. Comparando esto, por ejemplo, con Kepler, las señales de long cadence, que son 4 años, pues si aquí el nivel de significancia está, para encontrar pulsaciones significativas está en 0.7, eso mejora cerca de un factor 10 las observaciones de Kepler para estrellas de la misma magnitud. O sea, más o menos Kepler estará en 5 o 6 micromagnitudes, mientras que aquí bajaría nominalmente a menos de una amplitud de una magnitud.
Sí.
El factor sería 8.
¿Quién
Tengo 4 años observando el mismo cambio.
lo que pasa es que no estoy seguro de que ese nivel de ruido se refiere a un punto, ¿no? Yo creo que estas son simulaciones que hace Reza Samadi de la ratio ruido-señal, teniendo en cuenta las características de las observaciones durante todo, pues, 2 años, pues será lo que se obtiene después de integrar durante esos 2 años, ¿no? Claro, si eso lo llevas a un solo punto, pues entonces yo no creo que saliera esa tasa de ruido. Debería salir bastante menos.
¿Bastante mejor o bastante mejor?
Creo que bastante mejor.
O sea, incluso sería, entonces sí que mejoraría en las mismas condiciones para el mismo tipo de target, en orden de un factor 10 en la precisión de la target. O sea, el Kepler puede bajar más incluso a eso, a 6, o sea, tiene que encontrar señales por encima de 5 o 6 micromagnitudes de amplitud para que realmente sea significativo.
La parte que he quitado es la que está creando más interés.
More questions, Camila?
I just like to come up to from question. Were you referring to the mass radius and age, or were you referring to other parameters of the star?
Well, mass and radius are the typical ones to characterize later on the planet. And right now we are reaching current techniques with the set fitting or stellar spectrum. We reach about 10% of accuracy of these parameters. And there, of course, are related propagated to the planet parameters. So this was my question. With the level we will reach this asteroseismology with okay. Maybe you know. Yeah.
No. I don't. I was just like trying to understand what was the question about and the difference between TESS for the age determination.
Well, this is not using asteroseismology to characterize the star. We are using other techniques, like the star characterization using spectra or set fitting, but not asteroseismology. And this is where Plato will make a difference.
So
sorry?
You're not using gyro
But why do you compare with TESS? That's why I was saying that Plato is comparable to Kepler, because you cannot do those studies with TESS. So
there are Kepler studies with astrophysics studies to determine with solar-like stars, no thermodynamically excited solar-like stars, and you get to a 1 and a 2%. Is the last one you get with Kepler in some studies.
So this is
and I guess with these are some specific studies for maybe, I don't know, certain objects. Okay, and you get to this one.
For the age or the mass?
No, mass and the
So this level is amazing. If you can reach a level of uncertainty of 1% for these parameters, That it will be amazing.
But
Yes,
this is
yes.
as Javi said, you're going to go to different targets. You're going to go to targets that where Plato, the main core, is going to Earth like in the sense of 1 year orbits and that. So in the position, it's not the same when you have a Kepler target, but I don't know, solar light minute for year. So you're gonna have much better experience.
More comments? Okay,
Yeah.
Camila, that's
Uh,
like.
Do you know what's the maximum period of the planets that we can detect with a nominal emission?
Oh.
Or if some studies have been done on that.
The nominal mission will be point beams of 2 years. So you need at least three transits to claim a positive detection. So that's I don't know 8 months or 7 months. I think that's it.
So we don't get one.
But you can claim a detection with 2 transits. Actually.
With two transits.
Transits, and then you can reduce to half of the time.
Yeah, and some people do that with just 1 transit, but
No, but with 1 transit you cannot get the period. But with 2, yes.
yes,
With 2 you can have the period. And then you can at least have an approximate, which is the core period.
but
If you
there's
compare
no,
the depth of the transit, you can
there's
say,
no,
and the
no
duration, you
repetition.
can say that it's belong to the same planet.
I mean, the three transits is the minimum to say there's some periodicity, because if you have 2 transits, it's no periodicity. There is just two events repeated after some time interval.
No, but if you have a 1 year of observation, when you have 2 transits, and these transits agree in duration and shape, and then you have the event that belongs to the same planet, so you have a detection. So you need a longer observation to keep observing. Of course, but with 2 transit, and at least for this, 2 transit we are using to claim a detection for long period planet.
I don't believe those detection has a positive. I would say it's maybe a candidate, but not a positive detection with 2 points. And you can say with 2 points you can say whatever you want.
Whatever you want, you have a period.
No, because you have a period. Is the definition of a period is something that repeats after you don't have a repetition if you have two transits. There's no period. There is a time interval between 2 events. If they are flares or transits or any other or star pulsation, you don't know that.
I don't know. I think
we have other things that have really repeated the events, not only that we have track. That also and the duration. I think it's more philosophical.
Okay. More questions and comments? Bettina?
Yes, this can be delivered. It's like you said there were 50-second implications, but also 600 seconds. And so would we the delivery something like this that you have also the imaging target things it's defined to do
I know the images will be delivered, but I don't think that they are going to deliver the full frame images, the film.
So like for the light course, would be light course for all the statistical sample that will be done and will be which time stamp?
Sorry.
So the light course, which time stamp will they have, and are they for the statistical sample?
I think it's the statistical sample only. But you cannot have the full frame images, the full time, the timestamp of the full images, because these are really too big. So the satellite cannot save all this information.
And what will be the timestamp for the light course? 2.5 seconds, 25, 50?
2.5 is for the fast camera and 25 for the normal camera.
Great. I think we can close the seminar here. Thank you very much, Javier, for
Muy bien. ¿Qué tal? Son